Welcome, dear students, once again into the class of number theory. And today in this video, we will discuss some problems related to the Wilson's theorem, and then we will move on to the next chapter in the next video. So we will try to finish this chapter here in this video with some applications of Wilson's theorem. So let us start with some common and some very important applications of Wilson's theorem. So first of all, what the question I'm going to take is, the question is, if P is a prime, then show that P minus 1 factorial is congruent to P minus 1 modulo 1 plus 2 plus 3 plus and so on plus up to P minus 1. This we are to show using Wilson's theorem. So let us see how we'll move on to the proof. Here P is a prime, and we know that there is a distinct type of prime, that is 2. So for 2 we will see that the result is obvious. Why? Because if you put 2 here in this result, then 2 minus 1 factorial is congruent to 2 minus 1 modulo 1, and that means 1 is congruent to 1 modulo 1, which is obviously true. So there is no doubt, there is no question for this result. And now we will see the rest of the cases. That means when P is greater than 2, P is not an even prime, what will happen? So let P be greater than 3, the main case. In this case, first of all, look at this quantity. This 1 plus 2 plus 3 plus up to P minus 1. Using the sum of the arithmetic progression, you can easily show that it is equal to P minus 1 into P by 2. So directly or indirectly, we have to show that P minus 1 factorial is congruent to P minus 1 modulo. This is your P into P minus 1 by 2. This is actually we are to show. So for this result, now look that once again, that your P minus 1 by 2, P minus 1 by 2 divides P minus 1 factorial, because when you will expand this P minus 1 factorial, there will be a particular factor P minus 1 by 2. So P minus 1 by 2 divides this. Also, P minus 1 by 2 divides P minus 1. Actually, this is double of this. So this divides this. Now P minus 1 by 2 divides this, and P minus 1 by 2 divides this. That means P minus 1 by 2 divides their difference. And their difference means P minus 1 by P minus 1 factorial minus P minus 1. This is one thing. Secondly, by Wilson's theorem, your P is a prime. So P minus 1 factorial is congruent to minus 1 modulo P. And it is a linear congruence modulo P. So anywhere in this result, we can add or we can subtract a multiple of P. So that what is the key step? Here I am going to add one P. So P minus 1 factorial is congruent to P minus 1 modulo P, and that means your P divides P minus 1 factorial minus P minus 1. Now P minus 1 by 2 divides this quantity, P divides this quantity, and one thing is to be noted that the GCD of P minus 1 by 2 and P is 1, because P is a prime number and no number less than P can divide P, as P is prime. So their GCD is 1. This quantity divides this quantity also divides the same quantity, and their GCD is 1. That means their product will also divide this quantity. And what is the product of these two? The product of these two is P into P minus 1 by 2. this divides this quantity, and from this divisibility equation convert it into the congruence equation. What you will get? P minus 1 factorial is congruent to P minus 1 modulo P into P minus 1 by 2, and that is actually the result we wanted to obtain. So this is how we prove questions using Wilson's theorem. This is one question. Let us have some more questions, because I'll try to finish this chapter as I told you earlier. In the next video, we will be having new chapter, that is the arithmetic functions. So before going on to the next video, some more applications of Wilson's theorem we will like to have. Another question what I am going to take in this video: prove that 1 square into 2 square into 3 square and so on, P minus 2 square is congruent to minus 1 raised to the power P plus 1 by 2 modulo P, where P is obviously prime, because in number theory normally we denote prime numbers by P and other numbers by A, B, C or M and Q, X, Y, Z, but P particularly we keep it safe for prime number. So where P is a prime number. So let us see how to prove this result. So let us move on to the solution. P is a prime number, and by Wilson's theorem we know that P minus 1 factorial is congruent to minus 1 modulo P. This P minus 1 factorial, first I like to expand it. When you will expand it, what you will get? You will get 1 into 2 into 3 into 4 into and so on. At the end you will get P minus 1 congruent to minus 1 mod P. And since it is a continuous product, so before P minus 1 definitely you will have P minus 2, then P minus 3, then P minus 4. Now we will make pair of these terms. First of all, look at how many terms these are. These are P minus 1. So when you will make pairs of two terms from this expression, how many pairs you will have? You will have P minus 1 by 2 pairs. So I'll pair this with this. 1 into P minus 1. This is my first pair. Into this 3 with P minus 3. 3 with P minus 3. Then 5 with P minus 5. And so on, continuing like this. I will have in the last pair of 2 and P minus 2. Before that, I will have pair of 4 and P minus 4. And so on. So congruent to minus 1 mod P. Once again, it is a congruence equation modulo P. So that means any multiple of P can be added, can be subtracted from any term. So that what I am going to do. This is P minus 1. So this P is a multiple of P. So I can remove this P. That means I can subtract P from this term. Similarly, I can delete P from here. I can delete P from here. And from the last terms, in the first half, we will do the same process. From the last half, what we are going to do, this 2, I am going to write it, this 2 as 2 minus P plus P. 2 minus P plus P. So you can say, leave it. This is actually 2. This is 2. So just as I said you earlier, we can add P, any multiple of P, we can subtract any multiple of P. So why not to subtract p from here, so it is 2 minus p. Similarly, from this 4, I can subtract p, so it is 4 minus p, and so on. Now look at minus, how many pairs these are? This is one pair, this is second pair, this is third pair, and as I told you earlier, the last pair will be p minus 1 by 2th pair. So there are total p minus 1 by 2 pairs. Now in each pair, a negative sign is here, a negative sign is here, a negative sign is here, and if I write this 4 minus p as minus p minus 4, so a negative sign is here. This 2 minus p, I am going to write it as p minus 2 and minus outside, so a negative sign here. So how many negative signs are there? They are exactly p minus 1 by 2, because each pair contains one negative sign, and their product, that means minus 1 raised to the power p minus 1 by 2. And what you are left with now, look at, the first is 1 into 1, that means 1 square, into the second bracket 3 into 3, 3 square, 5 square, and so on. This minus is being counted here. So p minus 4 into p minus 4, p minus 4 square, and similarly p minus 2 square is congruent to minus 1 modulo p. Now we know that this is a linear congruence equation, and if a is congruent to b modulo p, then a and b both can be multiplied by any constant, and the congruence equation will remain okay. So this minus 1 raised to the power p minus 1 by 2, with this term I am going to multiply both sides of this linear congruence equation. So I am going to multiply this by minus 1 raised to the power p minus 1 by 2, and right hand side of this linear congruence equation again I am going to multiply with minus 1 raised to the power p minus 1 by 2. This minus 1 raised to the power p minus 1 by 2 into minus 1 raised to the power p minus 1 by 2, the power will be added. So p minus 1 by 2 plus p minus 1 by 2 will become p minus 1. So what you are going to get here is minus 1 raised to the power p minus 1. On the right hand side, minus 1 power p minus 1 by 2, and 1 power is there. So this 1 power will be added, this minus 1 will be removed, and you will get one more power here. Now what you are going to get now, this is minus 1 raised to the power even, because p is not a even prime, p is odd prime. Odd minus 1 is even, so minus 1 raised to the power even will become 1. So this term is going to be equal to 1. And multiplication with 1 will make no change into the term. So you will get 1 square, 3 square, 5 square. In the last you will get p minus 2 square is congruent to, on the right side, minus 1 raised to the power. When you will add these two powers, you will get p plus 1 by 2 modulo p, and this is our required result, what we are going to prove. So this is another question based on Wilson's theorem. Let us have a couple of more questions based on Wilson's theorem before ending this video. So let us have another question, very interesting question based on Wilson's theorem. Let a be an integer such that 1 upon 1 plus 1 upon 2 plus 1 upon 3 plus and so on plus 1 upon 23 is equal to a upon 23 factorial. If a is congruent to k modulo 17, what is k? What is the value of k? That means actually what we want to find, if a is divided by 17, what will be the remainder? Simply, in simple language. So let us start with this equation. When we start the solution, we will start with this equation. 1 upon 1 plus 1 upon 2 plus 1 upon 3 plus and so on 1 upon 23 is equal to a upon 23 factorial. First of all, multiply both sides by 23 factorial. So each term of the left hand side will be multiplied by 23 factorial. So you will get 23 factorial here. 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 And on the right hand side you will be left with only a. Then you will multiply by 23 factorial. Now, a is equal to this. If two quantities are equal, then they are definitely congruent to each other modulo any number. So that means a is congruent to this. So a is congruent to 23 factorial by 1 plus 23 factorial by 2 plus 23 factorial by 3 plus 23 factorial by 23 modulo 17. Because these two quantities are same, so they are congruent to each other modulo any number. So any number I am taking here 17. Now look that this first term is a multiple of 17 because 23 factorial will have 17 as a factor. So this is a multiple of 17, so can be removed. So I can remove this term. The second term, once again, it is a multiple of 17 because 23 factorial upon 2 will have 17 as a factor. So this can also be removed. Similarly, all the terms, even this term, only 23 will be cancelled and you will be left with 22 factorial. And 22 factorial also contains 17 as a factor, so it is a multiple of 17, so can also be removed. So you will be left with only one term. And what that term will be? That term will be 23 factorial upon 17 because all the other terms will have 17 as a factor. That means all of the other terms are multiple of 17. And you are working with modulo 17, so any multiple of 17 can be removed. So we are left with this only. Now 23 factorial over 17. Look at this now, what it is. So it is a is congruent to, when you will expand this term, you will get 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8, 9, 10, 11, 12, 13, 14, 15, 16, no 17 because 17 is cancelled, 18, 19, 20, 21, 22, 23, modulo 17. Now we will reduce the terms which are greater than 17. This 23, if you divide this 23 by 17, the remainder obtained will be 6. This 22 divided by 17 will give you a remainder 5. This 21 divided by 17 will give you a remainder 4. This 20 divided by 17 will give you a remainder 3. This 19 divided by 17 will give you a remainder 2. And this 18 will give you a remainder 1. Now, we will just try to reduce this. A is congruent to. Consider the first four terms, the product of first four. 1 into 2 into 3 into 4 is 24. And if 24 is divided by 17, the remainder obtained will be 7. So this whole can be replaced by 7. 5 into 6, 30 divided by 17 will give you remainder 13. 7 into 8, 56 divided by 17 again will give you remainder 5. 90 divided by 17 will give you remainder 5. 11 into 12, 11 into 12, it is 132 I think, yes it is 132, and 132 divided by 17 will give you remainder 13, so it is 13. Now I am going other way. 13 into 2, 26 divided by 17 will give you remainder 9. 14 into 3, 42, divided by 17 will give you remainder 8. 15 into 4, 60, divided by 17 will give you remainder 9. 16 into 5, 80, divided by 17 will give you remainder 12. So these terms are covered. What the term left is 6 into 6 modulo 17. So I will try further to reduce this. A is congruent to, once again, try to make pairs such that one of the terms is bigger and the other one is smaller, so that the calculation is very convenient. So I am taking this 7 with 9. 7 into 9 is 63. So 63 divided by 17 will give you remainder 12. So this is 12. 13 into 5, 65. When you divide it by 17, you will get remainder 14. Now once again 13 into 5, so again 14. Now 12 into 6, 72. When you divide 72 by 17, the remainder obtained will be 4. And another pair, the product is 72, so once again you will get 4 modulo 17. So more reduction is required. A is congruent to, once again, so 12, I am writing 12 as it is because other two pairs I am getting the same pairs, 14 and 4. So 14 into 4 is 56. When divided by 17, the remainder obtained will be 5. So 1 5 for this pair and 1 5 for the other pair. Modulo 17. A is congruent to this 12 into 5, 60, and divided by 17, remainder obtained will be 9. So 9 into 5 modulo 17, and now the last step, A is congruent to 9 into 5 is 45, and 45 divided by 17 we will get remainder 11. So 11 modulo 17. And now compare this with this one. In the question you are having A is congruent to K modulo 17, and here you are having A is congruent to 11 modulo 17. So comparing these two, we get K is equal to 11. So this is a very typical type of question, not so easy. A lot of calculation is required, but the basic thing is the use of Wilson's theorem. So another question now I am going to take, that is another question. If P is a prime, then P minus 1 factorial plus 1 is a power of P if and only if P is equal to 2, 3 or 5. That means what we want to say that P minus 1 factorial plus 1 is P raised to the power alpha if and only if P is 2, 3 or 5. So let us see whether the result is true for 2, 3 or 5. For 2, you are going to get here 1 plus 1, 2. So 2 is 2 raised to the power 1. The result is true. If you take P is equal to 3, so 3 minus 1 is 2, 2 factorial. And 2 factorial is 2, so 2 plus 1 is 3. So 3 is 3 power 1. No problem. If P is 5, then 5 minus 1 is 4. 4 factorial is 24. And plus 1, it is 25, which is 5 raised to the power 2. So that means this result is true if P is 2, 3 or 5. But now we are to show that this is not possible if your prime number P is greater than 5. So let let P be greater than 5, and if possible, let your P minus 1 factorial plus 1 is P power alpha. Another thing, this one you can take other side. So P minus 1 factorial is equal to P raised to the power alpha minus 1. Now look that P minus 1 divides P minus 1 factorial. Another thing, that by using Wilson's theorem, P minus 1 factorial is congruent to minus 1 modulo P. Now what actually I want to have, that P minus, so look that, another thing, P minus 1 divides this quantity, P minus 1 by 2 also divides this quantity. Why? Because P is odd prime. P should be here an odd prime. It should be an odd prime. So P is odd prime. Odd prime minus 1 is even divided by 2 is another integer which will be there in the factors of P minus 1 factorial. So P minus 1 by 2 divides this. Also 2 divides P minus 1 factorial. Now this number divides P minus 1 factorial, this divides P minus 1 factorial, this divides P minus 1 factorial. That means their product of this and this will also divide P minus 1 factorial. And what is the product? When we will take product of these three, 2 will be cancelled out and you will left with P minus 1 whole square. P minus 1 whole square divides P raised to the power alpha, divides P minus 1 factorial. But what is P minus 1 factorial equal to? P raised to the power alpha minus 1. Substitute it here. So P minus 1 square divides P raised to the power alpha minus 1. From here, we will have a very crucial, very important step. Suppose your P minus 1 is x. That means your P is x plus 1. So this will become x square. X square divides, here you will get x plus 1 raised to the power alpha minus 1. And when you will expand this using binomial theorem, x square divides x power alpha plus alpha x alpha minus 1 plus and so on. At the end of this expansion you will get the term 1, but there is minus 1 also. So 1 and minus 1 will be cancelled, and the second last term, that is some multiple of x, will be the last term now. So x square divides this term, and in fact here you will get alpha x. You will get alpha times something. Now x square divides this quantity. 1x from this and 1x from this term can be cancelled out. So that means x divides x power alpha minus 1. Here you will have alpha minus 2, and at the last you will have alpha. One thing is clear, that x divides this term, x divides this term, x divides next term. So that means x must divide the last term also. So x divides alpha. What was your x? X is P minus 1. So P minus 1 must divide alpha. So from this step we can deduce that P minus 1 divides alpha. And if P minus 1 divides alpha, that means P minus 1 is less than or equal to alpha. Is less than or equal to alpha. Also, look into this now once again. So this I am going to write here. P minus 1 is less than or equal to alpha. This result we have obtained. And now once again I am going into this result. P minus 1 factorial plus 1 is equal to P power alpha. So from here, P power alpha is equal to this P minus 1 factorial is 1 into 2 into 3 into 4 into and so on, P minus 1, and there is plus 1. So this means your P power alpha is definitely less than, because this 1 is less than P, this 2 is less than P, this 3 is less than P, and so on. You will have how many P's? The number of terms is P minus 1, so P minus 1 P's will be there, and plus 1. So that means P power alpha is less than P raised to the power P minus 1 plus 1. And definitely it means your P power alpha is less than P raised to the power P minus 2. And that means your alpha is less than P minus 2. And here you have a contradiction. One of the results says that alpha should be greater than or equal to P minus 1. The other result says that alpha is less than P minus 2. So they contradict each other. So you arrive at a contradiction. And why this contradiction is there? Because we have supposed that this is possible for P greater than 5. That means P minus 1 factorial plus 1 cannot be expressed as the power of P if P is greater than 5 and P is a prime. So this result is being proved. So here I am going to end this chapter. I am going to close this chapter. In the next video, I will be there with the next chapter, that means arithmetic functions. Till then, thank you. Thank you once again.